Welcome to the second part of our discussion on Arduino timers and analog to digital conversion. In this lesson, we'll introduce the Arduino analog to digital converters. Most of the real world cannot be represented by digital numbers. For example, let's say you had a voltage or temperature sensor, right? The data might look something like this. It'll be continuous in time and amplitude, right? It's an analog signal. Your microcontroller, however, computes via digital signals. And microcontrollers often have peripherals to facilitate translating between these analog and digital worlds. To go from this direction, you would use an analog to digital converter, often abbreviated ADC or simply AD. To go from this direction, you would use a digital to analog converter, often abbreviated DAC or DAC or simply DA. This is essentially the analog write functionality, where the Arduino uses pulse width modulation to produce a pseudo-analog signal. So let's explore the analog to digital conversion offered by the microcontroller on the Arduino. In the same way I was able to provide pseudo-analog outputs via the analog write command, I also have an analog read function, and this function takes a pin input and provides an integer output. On the Arduino, these 6 pins with the prefix A are my analog input pins. These are the 6 pins which allow me to perform an analog to digital conversion. The return values from analog read are dependent on the type of analog to digital converter on my microcontroller. So if I come over here and take a look at the datasheet for this microcontroller here, I'll see that I have a 6-channel 10-bit analog to digital converter. So there are 6 channels here, A0 through A5, and it's a 10-bit ADC. So that means my ADC can output 2 to the 10 or 10,024 possible values. In this case, since we're 0 index, we'll start at 0 and we'll go up to 1023. Now this is different than the 8-bit analog write command. When I'm writing pulse width modulated signals, that's 8 bits, so I can go from values of 0 up to 255. However, when I'm reading in analog values using my analog to digital converters, I'm 10-bit, so these values can take the range from 0 to 1023. Let's demonstrate this functionality using a circuit with a potentiometer or a variable resistor. A potentiometer has 3 terminals. The third one's known as a wiper, which is free to translate between both of the input and output terminals. And between the outer terminals, we'd measure the full resistance of the potentiometer, typically 1 or 10 kilo ohm. And if I move the wiper between either terminal, I'll measure a variable resistance. If I move the wiper all the way up to the input terminal here, I'll measure close to 0 ohms. And if I move the potentiometer down towards the output here, I'll measure the full 1 or 10K, let's say. The potentiometer is acting as a voltage divider then. And by putting this potentiometer into my circuit, I can tune the wiper position to change the resistance I'm measuring, which should ultimately give me a different value output from my analog to digital converter. So here's a standard voltage divider. I have a 5-volt input, and I have 2 resistors in series, R1 and R2. So the ratio of R2 divided by quantity R1 plus R2 will define the voltage output from my voltage divider. So if I were to measure, let's say, somewhere along the wiper location along my potentiometer, if I were to connect a wire from the output of the wiper to an input pin, say A3 on my Arduino, I would be able to tune the voltage measured by the Arduino by adjusting the wiper position of my potentiometer. So here's what a potentiometer looks like in hardware. You see the 3 terminals here, the third one being the wiper. And we see that by adjusting the wiper location, we're changing the effective resistance of the potentiometer, which will change the voltage registered by the ADC. Here's my circuit in Tinkercad. I have my Arduino Uno connected to a small breadboard. I have a green LED connected to a 330 ohm current limiting resistor, and that's connected to an output pin, pin 9. Here I have my potentiometer with my outer 2 terminals connected to 5 volts and ground, and then my third terminal, my wiper, is connected to pin A3 on my Arduino. With this setup then, my Arduino should be reading a variable voltage as measured across my potentiometer or variable resistor. So in one position, I'll be reading the full 5-volt drop across the full length of the potentiometer resistor. And in the other position of the wiper, I'll be reading 0 volts as the wiper will be effectively connected to ground. And I'll use this variable voltage as read by my analog to digital converter as a command to set the brightness level of my LED. Let's go ahead and run that, and then we'll take a look at the code. So here I'm reading the full 5 volts across my potentiometer, and I've written the code such that this illuminates the LED to the maximum brightness level. As I translate my potentiometer wiper from the top of my resistor down to the bottom or down to ground, I'll eventually set it such that I'm reading 0 volts across my potentiometer, and that corresponds to the least bright or the off position for my LED. Here's the code for my circuit. I begin by defining two integer variables, LED equals 9 for pin 9, and pot for potentiometer equals 3. That'll be pin 3, pin A3 on my analog to digital converters on my Arduino. In my setup function, I have two pin mode calls. I set LED or pin 9 as an output, and I set pot or pin 3 as an input. So for your analog inputs, you need to set a pin mode for those pins as an input. Then I initialize my serial stream to 9600 baud. In my loop function, I declare and initialize another integer variable that I call value, and that uses an analog read call to read in a 0 to 1023 value off of the potentiometer pin. So remember, the analog read is a 10-bit ADC, so those values could be anywhere from 0 to 1023. I then use that value variable as an input to an analog write call. So I analog write LED, that's the pin 9, and I write that to a value divided by 4. And I need to divide value by 4 since analog write is an 8-bit PWM output. So whatever value is reading will be anywhere from 0 to 1023. However, I can only analog write from 0 to 255. So I need to divide that value by 4. I print value to the serial monitor and delay for 50 milliseconds. And I loop through over and over again. So as I'm changing the wiper position on my potentiometer, my value as read in by analog read will be changing. Therefore, the brightness of my LED will be changing as my analog write command is changing. Let's take a look at both the circuit operation as well as the output from the serial monitor. My circuit is running and I'm monitoring the serial output in real time. My potentiometer wiper position is set such that I'm registering the full 5-volt drop across the potentiometer. So my analog read is reading a maximum value, and when I command pin 9, I'm getting a maximum brightness across my LED, and I see I'm getting 1023 out of my analog read. Great, so that's my max value. Now let's translate that wiper position slowly back. We should see the LED dimming as the voltage drop is reduced. And at some point, the wiper position will be connected to ground. Therefore, there's no voltage drop between the wiper position and ground. You see in my serial monitor, my analog read has decreased to 0, and the corresponding LED brightness has decreased basically to the off position for the LED.